Hi, everybody. My name is Tom Ihde. I'll be talking about the Chesapeake Atlantis model. I'll refer to that as CAM throughout the presentation. And I'll be talking about the design, parameterization, and applications in the past and the current application. CAM consists of 97 irregular polygons to represent the Chesapeake Bay. Those polygons are aggregated by depth, salinity, and in the main stem, bottom type to distinguish between hard bottom and mud. The purpose of the model is pretty broad. It's to understand likely fishery effects due to a range of habitat change going on in the Chesapeake Bay. The biogenic habitats included in the model are marsh around most of the fringing areas, submerged aquatic vegetation, and an oyster reef. And when the model was developed, it is based on 2014 code. That was before a lot of the restorations had taken place for oysters, and so oysters were pretty negligible at the time, and that may be an interesting future application to look at the effects of some of these restored areas, but that is not in the current application. The other major habitat concern in the Chesapeake is water column habitat and water quality, specifically nutrient and sediment coming down through the watershed through all these major tributaries. And the concentrations for those nutrients and sediment are provided by a pretty well-established 35-year monitoring network funded by EPA. And the loadings were provided from an EPA model known as the watershed model that aggregates those nutrients loadings based on simulated outputs considering land use, population trends, and the best management practices or BMPs that are in use. And what that has done for us is it allows us to simulate a range of attainment of what EPA refers to as the total maximum daily load of these nutrients and sediments that they require of each of the Bay states. And so we can fairly easily simulate attainment of their goals. And vertical structure, the first layer or the first meter of sediment is simulated along with some vertical layers. The 0 to 1 meter is essentially the photic zone in the model. Below this, the waters are too turbid to allow phytoplankton to survive. And 5 meters and 10 meter depths are essentially the top and the bottom of the picnic line. Coming into shore, about 2 meters of depth is about as deep as we'll ever see submerged aquatic vegetation or SAV growing, and about 10 meters in depth is about the deepest we see healthy oysters. River structure is important to understand because those loadings are dumped into the uppermost mid-channel box. So this is the James River and the York River. Obviously, quite a bit of different structure. The York is very shallow and long, and that's compacted into this fairly short tributary that represents the volume included in that river. We dump those nitrogen and sediment loadings into box 25, and in the York, we dump it in box 74. Hydrodynamics are driven by the Navy Coastal Ocean Model, or NCOM, that has about a 3-kilometer resolution. And to deal with boundary conditions, we use HYCOM, the Hybrid Coordinate Ocean Model. SAV input is based on the goals of the Chesapeake Bay program, which was essentially the maximum amount of SAV we saw historically. That equates to around the year 2000, mid to late 90s. And those different concentrations of SAV, which you can't really see in a map very well, of course, get spread out in our polygon structure. Marsh is based on observations from 2014, and a similar sort of deal, except marsh is even more concentrated around those fringing areas, and that's what we see in the polygon structure. The ecological groups are inclusive of fisheries of interest, of course, but also there are many prey species. Both vertebrate and invertebrate are about equally important in the Chesapeake Bay. And there's protected species as well, so those are included. And those biogenic habitats that we already talked about, and all the other things that are necessary to keep the system running in a representation of a reasonable structure and function. All those parameterizations are easily found online in the NoTech Memo that documents this, this model. And in that document, you'll also find a series of appendices that include the map information, the biological processes, and our rationales for parameterization, as well as 2 different sections with references that are specific to life history and diets. Very briefly, the past applications have focused on those habitat changes and the effects on the fish populations. Mainly SAV coverage and decrease, although we have simulated increase as well. But they're based on, again, those levels that inform the current watershed agreement for the Chesapeake Bay. These are essentially the goals for maximal SAV coverage, but the reality is we're losing SAV fairly rapidly due to temperature increase. Marsh coverage is again losing fairly rapidly around the Chesapeake Bay, mainly due to development and shoreline hardening. The comparisons that have been done looked at the different habitat changes independently and in combination. And that work suggests that temperature is by far the main driving factor of change that's affecting populations. The current application is a pilot study to build out the ecotoxicological application or module of the Atlantis, and it's focused on PFAS contamination, or per and polyfluoroalkyl organic compounds. These are man-made compounds that have been around since the 40s, but it's only recently that people have become concerned about PFAS in the environment, and they're the forever chemicals. They don't degrade. That's what they're designed for. And what has been found more recently is that they bioaccumulate in muscle tissues. So this can be a much bigger problem than anybody imagined, and the indications are these are very serious consequences, mostly toward infants, but there's also forms of cancer that are implicated for adults. Testing is super difficult and very expensive. PFAS chemicals are sticky, and that restricts the type of containers they can be sampled in, or the analytical quantification of them is what makes it really super difficult and expensive. The additional problem is the monitoring needs to be spatial. Thus far, monitoring is typically only done when there's a spill or a known input. And that's problematic because contaminated animals that are biomagnifying the chemical by eating their prey move. Unless you're bivalve, generally, this is, I believe, going to be a big problem. So consumption advisories are going to require multiple target species, in addition to many of those species are moving around. So this pilot study applies Atlantis to focus on a potentially much more cost-effective approach in estimating PFAS concentrations spatially for multiple species at the same time. And this is planned to be an iterative approach. The first species I'm working on is blue crab. Once we have those estimates, we'll go out in the field and ground truth those estimates and go back and tune the model to make sure the right magnitudes are being predicted, and then do it on a couple other species. The current planned species are striped bass and blue catfish and spot or croaker, which are popular recreationally fished animals. That funding has been provided by NIH, and just want to thank you guys for your attention. And please, if we don't get to talk about your questions during the conference, go ahead and email me, and maybe we can talk by phone.